Mark P. Otten back with you. All right, welcome to your very quick, well, we'll see how quick it is, very quick introduction to hypothesis testing for psychology research. It also may apply to other research, but we don't care about that. No, well, we do care about that, but we're probably, if you're watching this video, if you're in my class, you are a psychology student. So let's talk about it. Okay, so this is hypothesis testing is the part where we take our statistics and we try to make conclusions about them for research, for knowledge. We don't just do statistics for fun, although it is fun. Inferential statistics is like making a conclusion based on the probability that your data exists in the sample and does it exist in the population and stuff like that. So we'll talk about that translation here from samples to populations. When we do this, we can make our research poster, or we can write our research paper for our class or for a research conference or a journal, whatever. We can do this because the statistics fit into the scientific method in section 3, typically after well, you start with a hypothesis. The hypothesis goes in the introduction, usually at the end, and then you test the hypothesis with the hypothesis test is the statistics in the results section, and then you make a conclusion at the end in the discussion. And so the stats are like the mechanism that usually gets you from the hypothesis. Like, people make conclusions about stuff. They have opinions. They're just like, I think this. In science, that's great. That's a hypothesis, though. That's not like a fact. Or you can't prove stuff with hypothesis testing. But you can say, my data supports the idea that whatever. My data does not support the idea that whatever. So supporting theory or not is what we're after here. Now we can't prove stuff. Scientific method. Okay. So samples and populations I mentioned. Typically, the statistics come from a sample. Like, let's say we want to measure motivation in college students. We typically don't try to find every single college student in the world to sample on their motivation. We could try. It would probably not work. But we could try to find a sample of 20 college students at CSUN and then make a conclusion about them and then talk about, okay, does this apply to the population? If there's a finding, a particular statistical result in our sample, does that apply to a population? And so that's the process here that we're trying to, that's the concept of hypothesis testing that we're after. All right, so typically we have two hypotheses that we are comparing to each other. We're trying to see if we can support our null hypothesis or trying to see if we can support our alternative hypothesis. Usually we're trying to reject our null hypothesis. Usually let's say my hypothesis is that the more statistics you do, the more fun you're going to have. I mean, that's obviously true, but we have to, if that's my hypothesis and we're doing a test, we need to then gather some data and see if people enjoy statistics. If they do, great, then my hypothesis is supported. Cool. But if they don't, then maybe not. So in that case, the null hypothesis would be that the more statistics that you do, you will not have more fun. That's the reverse. That's where nothing is going on. That's where it's not interesting. You're sad if you don't get the result. Okay, so you're usually trying to reject the null hypothesis. By the way, that's a capital H with a 0 in the subscript. I've heard people say H-O. It's not really an O, it's a 0, and it's in the subscript, so slightly below the line of text. I don't know how people come up with this notation. But then we have the alternative, which is a capital H with a 1 in the subscript, which is even weirder. Like, it's the first hypothesis, but it's really just the one that you want to support, typically. And then, or there could be an A in there, which I think is a little better. Anyway, that's just notation, if you see it in the textbook, whatnot. This is the version of the hypothesis, like I said, where something is going on. If you reject your null hypothesis, then typically you can accept this one. So that's usually the goal. Not always, but usually. This is what they look like if there are two samples. So if we have two samples, let's say, of data, suppose we have a bunch of people who do statistics and a bunch of people who don't do statistics, and we want to see which group is having more fun. The first one, the mu, we're going to talk about this notation, but the first one's like mu1, that's the mean for people who, and the mu, let me show you this first. Okay, mu is a mu is a Greek letter, and it looks like a U with like a tail coming off the front, and it represents a population mean. So if we're making a hypothesis here, all the people in the world who are doing statistics, right? Population. So all the people in the world, not a sample, but everyone who are doing statistics are having more fun than people who are not doing statistics. So if we go back again, that's what this mu1 equals mu2 null hypothesis versus alternative with the unequal in the middle. The unequal means that people are having different amounts of fun if they're doing statistics versus not. The equal means that they're having the same amount of fun whether they're doing statistics or not. So those are the two. If one is true, the other cannot be true, right? And just a note about this notation stuff, like there's an X bar or an M, capital M, that you might see in research. That's a sample mean. And so if it's like an English language letter, you know it's a sample statistic. If it's a Greek letter like mu, or you might see this for standard deviation, there's like a sigma. If it's Greek, it comes from a population. I don't know who came up with this rule. But anyway, that's just a rule of thumb for you to help you navigate some of the textbook terminology and such. Okay, so we can also talk about directional versus non-directional null and alternative hypotheses. So I set this up as a non-directional situation. So by the example of the statistics and the fun, the null hypothesis is that people who are doing statistics are having the same amount of fun as people who are not. The alternative is that people who are doing statistics are having a different amount of fun than the people who are not. It's not saying they're having more fun, technically. It's just that it's different. It's unequals, right? I'm making the unequal symbol in the air. And unequal, so it could be that people who are not doing statistics are actually having more fun. That would be really unexpected. Anyway, I usually try to fit my example hypotheses to non-directional situations because that's the most common scenario for psychology research. There are directional ones, however, and the way I kind of set up this statistics example, it was that statistics, people who are doing stats have more fun. That's directional. That's that alternative hypothesis you see there. Mu1, people who are doing fun for people who are doing statistics, is greater than mu2, fun for people who are not doing statistics. Okay, so we have this chart. I've never really loved to spend too much time on this chart because how do you know if your hypothesis is really true or false? We can't prove anything here. But we can look at this alpha level and kind of move it around a little bit if we're concerned about getting it right. So there's two correct scenarios here and two incorrect scenarios. The top left is that I did not reject the null hypothesis. I accepted the null hypothesis and I was right. So this is the one where it's like, statistics students do not have more fun, and I was right. Sad. But I was correct. You reject the null hypothesis and it's really false. That's the lower right. And that's the happy one. That's like statistics students have more fun, and I was right. Woohoo! The data support. This is like, does my data support my conclusion? And if the answer is yes, then you're in the top left, or you're in the lower right. The other ones are errors, type 1 and type 2. You can see that type 1 is if you reject the null hypothesis and you're wrong. The other one is if you don't reject the null hypothesis, that's type 2, and you're wrong. So stare at that for a minute. I'm not going to probably emphasize this too much in my class, but all right, so what is a significant difference? Suppose the statistics students are having more fun than the non-statistics students, but it's like a slight difference. It's like average of 7 on a scale of 1 to 10 for one group, and in the other group it's 6. How do you know if that's significant? Well, psychologists have decided over the years, and most researchers doing this kind of hypothesis testing have decided that 5% or alpha of 0.05, is the cutoff. So this is just like an arbitrary decision based on lots of research over the years. Is it like a rule? No, it's just a guideline, I would say. In fact, you could potentially argue for a larger or smaller percentage here. But the theory is that if you get a difference in your sample, suppose your sample of statistics students is having more fun than the non-statistic students, then you're like, okay, there's a difference between my sample here, my statistic students, my non-statistic students. Suppose you take 20 of each, something like that. There's a difference there. But then when you apply it to the population, if there's if it's such a big difference, then it's unlikely that the population will be different than what you got in the sample. The sample is reflecting the population because, man, there's such a big difference. It must be the case in the population also that statistics people are having more fun. If the difference is small in the sample, then you're like, I don't know, small difference in the sample. We take it to the population. I don't know if it's going to hold up. And in that case, then it's probably a greater than 5% chance that it's not going to hold up. So then you would say it's a difference, but it's not a significant difference. So there's this statistical significance concept now that we push through our hypothesis tests. If alpha is 0.05, so that means that if there's a less than, then we're setting our probability at 5% there. If alpha is less than, or if our p-value is less than 0.05, then we are 95% confident that the statistical significance that we get from our sample is real or it can be applied to the population. 5% of the time it's going to be due to chance. The thing I will emphasize, and we're going to come back to over and over again, is the p-value, which the definition is the probability of the data given that the null hypothesis is true. What does that mean? If the null hypothesis is true, life is boring, statistics students do not have more fun, by our example. So, like, why are we concerned about this? Well, if the data does not support it, right? Like, given that statistics students do not have more fun, we have a huge difference in our sample between statistics students and non-statistic students. We have something. Oh, okay, now we can reject our null hypothesis if that p-value, if that probability is small. And like I said, we've set 0.05 as like this arbitrary cutoff, 0.5%. If it's less than that, well, if it's less than that, we'll just go with the rule here for our class. But feel free to be skeptical. Why is it 5%? Should it be 4%? How about 4.7%? I don't know. Feel free to be skeptical. But anyway, there's this triangle that I'll talk about when we get to the roadmap video. The triangle is there's three different things that are always equivalent. If the p-value is less than alpha, 0.05 typically, then the other two things are also true, and they all connect. So a test statistic, which we calculate for each test, that is greater than a critical value, which you can find online or whatever. You'll see all the details as we go through these hypothesis testing videos. P-value less than alpha, test statistic greater than critical value, reject the null hypothesis. All of those, one is true, the other two have to be true. Always. We'll keep coming back to that. And then the standard error comes in here. The standard error is like a descriptive statistic. With one sample, it's like standard deviation divided by square root of n. So, like, why do we talk about standard error? Well, standard error is our mode of translating our statistics from a sample to a population. So we have our sample means, we have our statistic students, we have our non-statistic students. We take the standard deviations of each one, and then we look at the sample size, the n. This is why sample size matters. In a large sample, the n is going to be gigantic, and then that sample is going to look more like the population. It's going to allow us to make stronger conclusions. And the statistical mechanism for accounting for that is the standard error, because the sample size is in there, square root of n. Technically, the standard error is the standard deviation of sample means. So it's like we have our sample means, and we're like, where would this fit into a bunch of other sample means? Like we're taking, let's say, samples of students at CSUN. I wonder if this would happen at UCLA. I wonder if this would happen at other schools. I wonder if this would happen with non-college students. Theoretically, those samples start to build up, and we need the standard error because it's the standard deviation of those sample means that we would get from lots and lots of samples that eventually would add up to the population. This is conceptual stuff. If you want to like just kind of proceed to the procedural, how do I run the test? Well, go to my other videos. This is the background. All right, so when we're talking about dividing by the square root of n, let's say with one sample standard error, you're dividing so that standard error becomes less than the standard deviation. And then the variation among sample means tends to be less than the variation among individual scores. So we're making this adjustment again to be able to translate our sample statistics to our population. Again, it's cool stuff. If you want to learn more about it, let me know. But for us, this translates to formulas. It translates to SPSS ultimately, and allows us to get that p-value. The p-value is the end result of all of this. Okay, so the test statistic, which I told you goes along with the p-value, it's going to be different for each different test that we run. That's going to tell us a little bit more about the situation as well. So it technically allows us to conclude how many standard errors, how far away from the population mean is our sample mean, or how far away from the null hypothesis is our data. And if it's far away from the null hypothesis, then we reject the null hypothesis and conclude that our data is supporting the alternative. Again, a little bit more theory here. If our sample mean, this is like a two sample example. So if we have two samples and our sample means are different from each other significantly, not just different, but significantly different by our statistics, then we reject our null hypothesis, and we have this little thing where the p-value is less than alpha. If that's true, then the test statistic is always greater than the critical value, and we reject the null hypothesis. So, given that, a few guidelines for what a good hypothesis might look like. Number one is that it was created by me. Well, just kidding. Okay, these are the real guidelines. These are taken from statistics textbook. I forgot which one, but I've adapted these notes from textbooks I've read over the years. So these are some guidelines for how to make a good hypothesis. It's not too complicated. So number one is it states an expected relationship between variables, between groups, between psychological constructs. So this is what you're expecting. I expect that people who do statistics have more fun than people who don't. So your variable there would be like fun, and then like two groups being compared on fun based on whether they do statistics or not. Fairly straightforward, right? But then if we started adding in multiple stuff, it starts to get more complicated, and we can do that, but then we violate number 3 because it's no longer brief and to the point. So I hypothesize that people who do statistics have more fun if they are in Dr. Otten's class, but only in the month of October, because in the month of October he covers chi-square tests, which is super fun, but when he covers t-tests it's not as fun, so I don't expect that. But also he's teaching online, so when he doesn't teach online it's not as fun. Okay, so you can add those layers to a hypothesis, but then people, like, it's going to be not only harder to read, but harder to test statistically. So, okay, so brief and to the point, number 3. States an expected relationship, number 1. Number 2 is like research methods, scientific method. Typically, you need to figure out where your theory, it's good to have a theory that nobody's had before, nobody's studied before, but then you got to position it like within the theory or the literature that already exists. If you do that, that's not typically part of my statistics class. It's more like a research methods class task, number 2, but it has to be done in order for you to be able to present at a scientific conference or submit for your thesis or whatever. So number 2 is good in general. And the number 4 is like it's possible to test. So I believe that people who do statistics have more fun when they live on Mars. Well, you can't test that. So unless we find people on Mars, I don't know. Like we haven't yet, but maybe by the time you're watching this video, we will have found life on other planets. Okay, so that's your quick introduction to hypothesis testing. I hope it was quick. Maybe I talked too much.